Welcome back to the deep dive into the Neural Intel podcast. Okay, let's jump right in. You've got these amazing large language models, right? LLMs, and you can nudge their behavior with just a simple prompt. But while that change is often temporary, it's like writing on water almost, then you've got fine tuning. That makes changes permanent, sure, but it's this massive effort, like carving a whole new sculpture from stone. So what if there was a way to kind of get the best of both? Take those temporary prompts and, I don't know, bake them right into the model's core, make them stick. Today, we are diving into a really fascinating new paper. It's called prompt baking, and it proposes exactly that, a technique to turn a prompt into a permanent weight update for an LLM. Our sources for this deep dive come from researchers at Caltech and the University of Toronto. They're really pushing the boundaries on how we interact with and control these models, focusing, as we like to do here, on the technical nitty-gritty and the implications. So, okay, what does this actually mean for you, the listener? Maybe you're trying to get an LLM to consistently follow instructions or hold a specific persona, or even just remember some new piece of info. Traditionally, you've got two main paths, right? There's explicit prompting, natural language, easy, but like we said, temporary. And then there's weight updates, fine tuning. That's permanent, but it's implicit, data driven, and prompts often, well, they fade. They decay over a conversation. Plus, trying to teach precise knowledge just through data examples, that can be really tough. This paper, it seems to offer a third option.
It really does. And the core idea, it's got this mathematical elegance to it, actually. Prompt baking takes an initial set of LLM weights, let's call them theta, yeah.
Right.
And it takes a prompt, U, and it converts them into a new set of weights, which we can call theta U. The whole goal is to make the LLM with these new theta U weights behave exactly as if it's always being prompted with U, even when, U isn't explicitly given anymore.
Okay, so it's like embedding the instruction directly into the model's parameter.
Precisely. And they achieve this by minimizing something called the KL divergence, DKL.
Yeah.
It's basically a way to measure how different one probability distribution is from another. In this case, it's about matching the output probability distribution. So what the model is likely to say next between the original model when it's prompted and this new baked model. Specifically, they're matching the logits.
Ah, logits. Okay, so just to make sure everyone's following, logits are like the raw scores, right? The model's
Yeah.
internal, unnormalized scores for every possible next word or token before they get turned into actual probabilities.
That's exactly it. Think of it like this. Think of it like this. If you ask, what color is the sky? The logits would have a huge score for blue and, tiny scores for banana or table.
Yeah.
Prompt baking works by making sure the baked model's internal scores, its logits for every possible next word, are almost identical to the original model's scores when it had the prompt.
Okay.
And this isn't just like theoretical math. They actually do this using gradient descent. They approximate that KL divergence measure statistically using Monte Carlo sampling of generated text sequences.
Right, so standard machine learning optimization techniques, but applied in this clever way to match the prompted behavior.
Exactly. And here's where it gets really practical and honestly quite impressive.
Yeah.
They found they can often do this super quickly, sometimes in as little as 5 minutes, using something called LoRa adapters.
Wow, 5 minutes. Okay, LoRa adapters, for those maybe not super deep in model architectures, those are like small, efficient add-on modules. They let you update parts of a giant model without retraining the whole beast.
Right. You got it. Think of them as specialized chisels. They let you make these precise changes, bake in the prompt, without the massive computational cost of recarving the entire statue. It makes it feasible.
That speed is definitely a game changer.
Totally. And to help visualize it, the paper uses this great example. Imagine you want an LLM to always be negative, like an always sad persona. They show how the baked model's tendency towards negative sentiment just smoothly increases during baking until it perfectly matches the prompted baseline model. It's this smooth behavior interpolation that's really key.
So it learns the vibe, not just specific words.
Exactly. And they show this at the token level too. Before baking, the unprompted model might say something positive. But after baking, the now unprompted baked model spits out depressing words, perfectly aligning with what the original model would have said if it had the be sad prompt. It's like its internal mood is aligned.
That's seriously cool. It works in principle, it works fast. But let's talk brass tacks. What can you actually do with this? What are the real world wins, especially for, complex stuff?
Yeah, good question. So one of the big payoffs they demonstrated is baking in complex reasoning patterns, specifically chain of thought.
Ah, chain of thought. That's the technique where you prompt the LLM to think step by step, right? Break down problems. Usually helps accuracy a lot on reasoning tasks.
Exactly that. What they showed is that baking in few-shot chain-of-thought prompts with just a few examples of step-by-step reasoning on tough academic benchmarks. Things like GSM-8K for math word problems, ASDiv, MBPP for coding, ARC, Common Sense QA. Baking the COT prompt gave almost the exact same performance boost as actually using the few-shot prompt during inference.
Almost the same. How close are we talking?
We're talking within 1.4% accuracy on every single one of those benchmarks compared to the standard few-shot prompted model.
Wow. Okay, that 1.4% across the board isn't trivial. It means the baked-in reasoning is basically just as good as having the prompt there live. It's like teaching it the skill permanently.
Pretty much. It learns the process.
Yeah.
And on GSM-8K specifically, even the zero-shot performance of the baked model, meaning no prompt at all, showed significant gains over the original unprompted model. But here's where it gets kind of wild.
Oh, go on.
On some benchmarks, if you take the model that already has the prompt baked in, and then you reprompt it anyway with the same chain of thought instruction, shockingly, it actually does better than just prompting the original model.
Wait, hold on. Let me get this straight. You bake in the prompt, then you prompt it again on top of the baking, and it performs even better than just prompting the original model once.
That's what they found.
How is that even possible? Like amplification?
That's the term they use, prompt amplification. It suggests baking doesn't just embed the instruction, maybe it sensitizes the model, makes its internal pathways more receptive, so the next time it sees the prompt, it resonates even stronger.
That's genuinely mind-blowing.
Yeah. For GSM-8K, using this amplification effect, they actually beat Meta's published Llama 3 accuracy by 1.4% using the same base model and setup.
Okay, that's not just interesting, that's a significant result. Beating published benchmarks is a big deal.
Absolutely. And it's not just instructions. They also successfully baked in new knowledge.
Ah, okay, so facts, not just behaviors.
Right. They took recent news headlines the model definitely hadn't seen during training, things like Pavel Durov's arrest and release back in August 2024. They sequentially baked these facts into the model, and afterwards the model could recall this information, even when asked indirect questions about it.
That tackles the context window problem, potentially. You don't need to stuff breaking news into the prompt if you can just bake it in quickly.
Exactly. It suggests a path to keeping models updated without constant retraining or relying solely on massive context windows.
And what about that prompt decay issue? The model forgetting its instructions halfway through a chat.
Solves it. Pretty effectively, it seems. Baked models maintain their persona or instruction stability much better over long dialogues. You know how chatbots can start strong and then kind of drift off topic or forget their persona?
Oh yeah, the digital exhaustion thing. Starts helpful, ends up monosyllabic.
Well, baking seems to prevent that persona drift. The baked-in behavior remains near constant, whereas traditional prompted models show that decline. Figure 7 in the paper shows this really clearly.
That alone would be huge for so many applications. Customer service bots, long-form content generation.
For sure. And another really neat aspect is what they call half-baking.
Half-baking, like stop the process early.
Exactly. By stopping the baking gradient descent process partway through, you can create models with intermediate levels of the prompt's influence. This gives you continuous control over the model's behavior intensity. It addresses a long-standing headache in prompt engineering, where getting subtle, fine-grained control is often really tricky. You either have the prompt or you don't. This gives you a dial.
A behavioral dial. Interesting.
And one last major benefit ties into the bigger picture of AI development. Catastrophic forgetting.
Right, the classic problem. Teach a model something new and it wipes out something it learned before.
Yep. They did preliminary tests baked in one prompt, then checked if the model bombed on unrelated tasks it previously knew. The results. Prompt baking showed remarkable resistance. Performance on unrelated tasks barely dipped, like 3.4% accuracy drop at most. This suggests you might be able to continually bake in new prompts, new knowledge, without destroying existing capabilities.
That's huge for continual learning. A model that can learn without forgetting, that's a holy grail. Okay, so we've seen the results, the performance boost, the knowledge updates, the stability, this amplification thing. It's clearly powerful. But now let's really dive deep. Let's pull back the curtain. How does this work under the hood? What's happening inside the network? And what does it tell us about LLMs? Maybe even about cognition itself.
All right, so digging into the mechanics, the technique definitely builds on ideas from model distillation. But it's a specific kind. Maybe think of it as self-distillation. The model is essentially distilling its own behavior when prompted. It also neatly extends concepts from LLM control theory. It's projecting those changes in probability distributions caused by the prompt directly onto the model's weight space.
Okay, projecting probability changes onto weight space.
Yeah, and that half-baking thing we mentioned, it suggests the model is moving along what they call functionally invariant paths in this massive high-dimensional weight space.
Functionally invariant paths. Okay, unpack that a bit. Does that mean there are specific ways to tweak the weights that change only the targeted behavior without messing up everything else, like finding a safe route through a minefield?
That's a pretty good analogy, actually. It implies there are structured ways to modify the model's function space by moving through its weight space, allowing for that fine-grained continuous control we talked about, not just random weight changes.
And why the focus on KL divergence and the full logit distribution? Why not just match the top few predicted words, for example?
Great question. The paper really emphasizes this. Using the full distribution of logits is crucial for the baked model to generalize well. They found there's a kind of critical threshold. You need to match a certain number of logits for the baked model to really capture the essence of the prompt and apply it broadly. It suggests an inverse relationship. The more complete the logit distribution you match, the less data you might theoretically need to achieve generalization.
So capturing the model's full range of maybe options is key, not just its top choice.
Exactly. And another fascinating point is that prompt baking seems naturally resistant to overfitting.
How so? Usually fitting something specific risks overfitting to it.
Well, unlike traditional fine-tuning, where you're maximizing the likelihood of the model producing outputs from some external data set, here you're minimizing the divergence between two versions of the same model, the prompted one and the unprompted one being baked. This means the weight updates tend to be compatible with the original model's weights. They stay close in the weight space, which helps preserve the model's general knowledge and abilities. It's not trying to memorize an external data set.
That makes sense. It's learning from its own prompt itself, not from outside examples.
Right. And tying back to that sad model example when they did half-baking, the model didn't just randomly switch between neutral and super sad. It consistently produced moderately sad content. This suggests the model isn't just memorizing endpoints. It's traversing a path in its weight space that corresponds to a semantically meaningful interpolation to the behavior. It understands degrees of sadness implicitly.
It's learning the concept, not just the command.
It seems that way, which leads to some really intriguing, though obviously speculative, parallels with human cognition they mentioned.
Ah, the System 1, System 2 idea.
Yeah. They suggest that behavior driven by an explicit prompt is like Kahneman's System 2, thinking it's slow, deliberate, takes active effort, computationally expensive for the model. They mention owing to complexity related to attention. Prompt baking, then, is like converting that effortful System 2 process into fast, automatic, intuitive System 1 thinking, minimal overhead once it's baked in.
So turning conscious effort into ingrained habit or skill.
Kind of like that, like turning short-term explicit instructions, remember to carry the one, into durable implicit knowledge or skill. I just know how to add. They also connected to the credit assignment problem in neural nets. How do you know which specific synapse or weight contributed to a high-level success? Prompt baking allows these high-level natural language instructions to directly influence synapse-level updates via the KL divergence objective.
That cognitive analogy is powerful. It makes the whole process feel less like just a technical trick and more like, well, a form of learning, albeit an artificial one, converting deliberate thought into intuition.
It's a compelling way to frame it. But there are still open questions, things the paper touches on but doesn't fully resolve. One big one is commutativity.
Meaning, does the order in which you bake things matter?
Exactly. What happens if you bake in conflicting information? They tested this. So you first bake in Joe Biden staying in the race. Then you bake in Joe Biden is dropping out. They found the order does matter significantly for contradictory prompts. The final state of the model depends on which conflicting piece of information was baked last. It's non-commutative.
So the model's history, the sequence of baking, leaves a trace. It's not just overwriting.
Right. And this non-commutativity with conflicting inputs reminded the researchers, and this is pretty mind-bending, of non-commuting measurement operators in quantum mechanics.
Whoa, okay. Quantum mechanics, that's unexpected. Are they suggesting LLMs have quantum properties?
No, not literally. It's more of a mathematical analogy. In QM, measuring spin along the x-axis, then the z-axis gives a different result than measuring z than x. The order matters. They're suggesting that perhaps the way information interacts and integrates within the LLM's complex weight space has analogous mathematical properties, where sequence is fundamentally important for conflicting inputs. It definitely opens up avenues for exploring the deep internal dynamics.
That QM connection, even as an analogy, is wild. It really underscores how much we still don't fully understand about what's going on inside these vast
For
networks.
sure, it warrants a lot more exploration.
So, wrapping this up, from boosting complex reasoning to instantly updating knowledge, preventing that annoying persona drift, even this wild amplification effect, prompt baking really feels like a fundamental shift, a new tool in the toolbox for how we interact with and shape LLMs. It's taking something we always thought of as ephemeral, the prompt, and making it a durable, baked-in part of the model's actual structure, its being, if you will. And it leaves you with a pretty provocative thought, doesn't it? Consider this. If we can bake in a prompt, turn a temporary instruction into core behavior, and even amplify it by baking again, what are the ultimate limits here? Could we one day define entire complex personalities, skill sets, expertise for an AI agent just by writing a few well-crafted sentences and then hitting bake? Where does that lead? Lots to think about there. And if you want to stay updated on the latest research papers like this one in AI and ML, definitely check out our webpage. The link is, as always, in the bio. Thanks for diving deep with us on Neural Intel.